The forest floor appears stable at first glance, a mosaic of decomposing leaves, exposed buttress roots, and fallen branches that have softened under months of humidity and microbial digestion. The air hangs heavy, saturated enough that each breath feels textured, as though inhaled through damp cloth. Above, the canopy filters sunlight into shifting columns that drift with the movement of high leaves, illuminating patches of ground in brief, almost theatrical clarity. Within this layered system, beneath bark and inside hollow stems, entire societies operate without spectacle. The bullet ant, Paraponera clavata, moves among them, large, dark, deliberate, its body glossy like polished obsidian. It does not scurry in nervous zigzags like smaller ants. It walks with a measured, almost indifferent pace, as though it understands that its defense requires no haste. Your foot compresses the leaf litter near the base of a tree whose trunk is alive with subtle traffic. Bullet ants often nest at the roots of trees, forming colonies that can number in the hundreds. Their presence is not announced with visible mounds, but with quiet patrols along bark and vine. Many tropical trees host extrafloral nectaries, small glands that secrete sugar outside of flowers, and these attract ants that in turn defend the tree from herbivorous insects. In some cases, the relationship is loosely mutualistic, in others, opportunistic. Bullet ants may forage widely, but they are attentive to disturbances near their nest entrance. A vibration in the substrate, the compression of soil, the chemical trace of mammalian skin, these are signals in a sensory world built on touch and scent rather than sight. The sting arrives with a precision that belies its scale. The ant anchors itself with its mandibles and drives its stinger into skin. Unlike bees, bullet ants do not lose their stingers. They can sting repeatedly. The venom contains a neurotoxic peptide known as ponerotoxin, which interferes with voltage-gated sodium channels in nerve cells. These channels regulate the propagation of electrical signals along neurons. When disrupted, they misfire, generating intense and sustained pain signals. The initial sensation is sharp and electric, but within seconds it expands into a radiating wave that feels disproportionate to the size of the wound. Pain researchers often describe this sting as among the most intense in the insect world, not because it causes tissue destruction on a massive scale, but because it manipulates neural signaling with ruthless efficiency. Your body reacts before cognition fully assembles the event. The sympathetic nervous system surges into dominance, releasing adrenaline and noradrenaline into the bloodstream. Heart rate accelerates. Blood vessels in the skin constrict and then dilate in uneven patterns. Sweat glands activate, attempting to cool a body that has interpreted the event as a severe threat. Shaking begins, not solely from fear, but from the rapid firing of motor units under stress hormones. The field of vision narrows into tunnel focus as blood flow prioritizes core organs and large muscle groups. This is a survival reflex shaped in environments where sudden pain might signal predator attack. The forest, however, is not always attacking with teeth. The second mistake unfolds in the instability created by this reflex. As balance falters under the surge of shock, your hand reaches instinctively for support. In a rainforest, vines are abundant, roots twist above ground, and tree trunks provide apparent anchors. Yet these surfaces are not neutral. Many are highways for ants, beetles, and other invertebrates. The vine you grip may carry additional bullet ants returning from foraging, or it may belong to a plant species whose smooth bark conceals hidden cavities housing colonies. By grabbing without looking, you introduce your skin into another defended perimeter. A second sting compounds the first, and the pain intensifies in overlapping waves. Alternatively, the sudden contraction of muscles and the disorientation from pain may cause you to lose footing entirely. The forest floor is uneven, layered with decaying wood that can collapse under weight. A fall onto a root or stone can drive air violently from the lungs, producing the familiar but alarming sensation of being unable to inhale. For a brief interval, the diaphragm spasms, and the body struggles to re-establish rhythmic breathing. In this moment, the line between neurological shock and mechanical breath loss blurs. The sting did not directly steal oxygen, but it set in motion a cascade that compromised coordination and posture, leading to secondary injury. Pain forces hyperventilation through intertwined pathways. Intense nociceptive input stimulates regions of the brainstem involved in respiratory control. At the same time, anxiety and stress hormones heighten respiratory drive. Breathing becomes rapid and shallow, increasing the rate at which carbon dioxide is expelled. When carbon dioxide levels in the blood drop too quickly, blood pH shifts toward alkalinity in a condition known as respiratory alkalosis. This chemical change can produce dizziness, tingling in extremities, and further destabilization of motor control. Ironically, the attempt to breathe more in response to pain can reduce the efficiency of oxygen delivery to tissues by altering hemoglobin's affinity for oxygen. Decision-making suffers because the prefrontal cortex, responsible for executive function and risk assessment, is sensitive to both stress hormones and fluctuations in blood chemistry. Within the colony, the sting is not an isolated action, but part of a coordinated defense. Bullet ants release alarm pheromones when disturbed, chemical signals that recruit nearby workers to the source of threat. These pheromones diffuse through the air and along surfaces, invisible but potent. Additional ants converge, not randomly, but along established foraging trails mapped by chemical cues. The colony operates as a distributed nervous system, each individual responding to gradients of scent intensity. The human nervous system, overwhelmed by one sting, struggles to process the escalation, while the ant colony's collective response remains organized and adaptive. Ecologically, bullet ants occupy a niche that blends predation and defense. They hunt other arthropods, subduing prey with their sting and powerful mandibles. In doing so, they regulate insect populations in the understory, influencing herbivory rates on plants and indirectly affecting plant growth dynamics. Their large size and potent venom deter many vertebrate predators, although some specialized species, including certain birds and small mammals, may exploit moments when the ants are less active. The ants' diurnal activity patterns are shaped by temperature and humidity. Excessive heat can desiccate smaller insects, but bullet ants, with their relatively larger body mass, manage water balance more effectively. Thermoregulation in insects relies heavily on behavioral adjustments, seeking shade, altering activity periods, and selecting microhabitats with favorable humidity gradients. As you attempt to steady yourself, hyperventilation continues. The rapid breaths feel necessary, yet they amplify dizziness. Fine motor control degrades, fingers tremble, grip weakens. The concept of self-rescue becomes distorted. Instead of slowing movements and scanning surroundings, the urge is to move quickly away from the source of pain. In doing so, you may brush additional vegetation, step into uneven ground, or collide with branches. The forest does not need to actively pursue you. Your own physiology, hijacked by pain, increases the likelihood of miscalculation. There is a stark efficiency in this dynamic. The bullet ant does not rely on venom that paralyzes or kills large mammals. It relies on pain as a deterrent powerful enough to rewire behavior. Pain is expensive in metabolic terms. Producing venom requires energy, and stinging exposes the ant to risk. Yet the payoff is substantial. A large animal learns to avoid the nest area, reducing trampling and predation. From an evolutionary perspective, the sting is less about immediate incapacitation and more about long-term behavioral modification in potential threats. Hours after the sting, waves of pain can persist, sometimes described as throbbing or pulsing in synchrony with heartbeat. Inflammation spreads locally, but systemic toxicity in healthy adults is rare. The primary impact is neurological and psychological. The memory of the sensation embeds deeply, shaping future decisions. In indigenous cultures of the Amazon, bullet ants are famously incorporated into initiation rituals, where controlled exposure to stings serves as a test of endurance. The ritual context underscores a biological truth. The pain is intense yet survivable, a testament to the precision of the venom's design. The rainforest resumes its steady rhythms around you. Birds call from mid-canopy perches, frogs vocalize from hidden pools, and the leaf litter continues its slow transformation into soil through the work of fungi and detritivores. The bullet ant colony retreats to routine once the disturbance subsides, workers returning to forage, larvae tended in subterranean chambers. The episode leaves behind no visible scar on the forest, yet it illustrates a principle woven through tropical ecosystems. Defense mechanisms often operate by exploiting universal physiological pathways. Pain, breath, balance. These are shared vulnerabilities across species. In this environment, coordination is survival. When pain hijacks coordination, the threat multiplies beyond the original sting. Hyperventilation clouds judgment, adrenaline narrows perception, muscle tremors undermine stability. The forest's complexity demands measured responses, yet the nervous system under acute stress pushes toward urgency. The lesson embedded in the sting is not merely that the ant is dangerous, but that biological reflexes, adaptive in one context, can become liabilities in another. The rainforest does not always overpower through size or force. Sometimes it leverages the architecture of the nervous system itself, turning the body's own alarm signals into a cascade that, if unchecked, edges towards self-destruction. The riverbank at dusk carries a stillness that is not absence but compression. Cicadas wind down from their daytime crescendos, replaced by the low percussion of frogs in oxbow pools and the faint splash of fish breaking the surface. The air smells of tannins and wet clay. Along the margin where forest meets water, sand holds impressions, tapir tracks, capybara prints, the splayed marks of caiman sliding in and out of the shallows. Above, the canopy braids light into ribbons that drift and dissolve as evening thickens. It is in this threshold space, where prey must come to drink and predators can approach through cover, that the realization arrives. You are not alone, and you are not first to notice. The sensation is subtle at first, a shift in attention without visible cause. The mind registers pattern before the eyes confirm it. Somewhere within the understory, leaves do not simply sway, they settle with intention. A patch of rosetted shadow remains still when wind stirs everything around it. The jaguar does not announce itself with a roar in these moments. It relies on silence and proximity. Its coat, patterned with rosettes unique to each individual, fractures its outline against the mosaic of sunlit leaves and darkness. Unlike many big cats, the jaguar is compact and heavily muscled, built for explosive power rather than prolonged pursuit. Its territory may span dozens of square kilometers, overlapping river corridors and forest interior, but its hunting strategy compresses time and space into seconds. Breath spikes before movement. The autonomic nervous system responds to perceived threat with a surge of adrenaline. Heart rate accelerates, muscles tense, peripheral vision sharpens while central focus narrows. This narrowing can be adaptive when immediate action is required, yet in dense rainforest it can also obscure context. The mind fixates on the shadow that might be a cat, reducing awareness of roots underfoot or branches at head height. Breathing becomes audible, each inhalation drawing humid air deep into lungs already working harder in saturated heat. Jaguars hunt through stealth and ambush rather than chase. They move along game trails and riverbanks where prey density is high, using cover to close distance. Their bite force is among the strongest relative to body size of any big cat, capable of penetrating skulls or the armored hides of caimans. This anatomical power is paired with patience. A jaguar may observe for minutes or longer, reading posture, wind direction, and spacing. It hunts not merely bodies, but moments when prey is distracted, when footing is compromised, when escape routes are limited. The second mistake unfolds in the human body's attempt to resolve uncertainty. Turning your back to run through thick understory aligns with prey behavior. Many ungulates bolt at first sign of danger. Jaguars are adapted to capitalize on that reaction, launching in short bursts that cover surprising ground. Running in a straight line is rarely possible here. Vines catch at ankles, roots arch unpredictably, and visibility collapses into green walls. A sprint amplifies noise, branches snapping, breath rasping, broadcasting location. Alternatively, freezing in the wrong spot, perhaps silhouetted against open water or standing atop a rise, can create a clear target if distance is already minimal. Even without a full attack, panic reshapes the environment. A backward step without scanning can send a heel sliding on damp clay. A stumble forward may drive palms into gravel or thorn. Cuts open on forearms. Blood scent mingles with river air. The jaguar's olfactory sense is less emphasized than its vision and hearing, yet any noise or erratic motion can recalibrate its assessment. Predators are energy economists. They weigh risk against reward. A confident, upright presence that maintains eye contact and moves deliberately may signal difficulty. A chaotic retreat signals vulnerability. The Amazon's humidity plays a quiet role. Air heavy with moisture impedes evaporative cooling, so breathlessness arrives quickly under stress. Hyperventilation alters carbon dioxide levels, producing dizziness and tingling that undermine coordination. Oxygen debt accumulates in muscles that tense and release repeatedly. The jaguar, by contrast, is built for short, explosive exertion followed by rest. Its thermoregulation relies on shade, panting, and proximity to water. It often hunts near rivers, not only because prey congregate there, but because water offers cooling and escape routes. In floodplain forests, seasonal changes alter prey distribution, and jaguars adjust movement patterns accordingly, tracking migrations of capybara, deer, and peccary. The cat's sensory adaptations are tuned to this environment. Its eyes, large and forward-facing, provide binocular depth perception, crucial for gauging leap distance. The tapetum lucidum enhances low-light vision, allowing it to operate effectively at dawn and dusk. Whiskers detect subtle changes in air movement. Padded paws distribute weight silently across leaf litter. Each step is placed with calculation. When it closes distance, it does so with minimal warning. From an ecological perspective, the jaguar is a keystone predator. By regulating populations of herbivores and mesopredators, it influences vegetation structure and trophic cascades. Its presence shapes behavior across species. Peccary herds alter movement patterns in areas of high jaguar activity. Capybara remain alert at water margins. Even smaller predators may adjust hunting times to avoid overlap. The forest's structure, dense understory, braided waterways, fallen logs, creates ambush opportunities that the jaguar exploits with anatomical precision. The escalation in a human encounter often occurs not through direct contact, but through amplification of mistakes. A fall that knocks breath out leaves the chest heaving, each inhalation loud in quiet forest. The diaphragm spasms, delaying recovery. In that moment, noise becomes involuntary. Leaves scraped by scrambling hands mark location. The cat, already attuned to subtle cues, recalculates. It does not need to chase if the environment and physiology are already eroding composure. In many documented encounters, maintaining eye contact, appearing larger, and backing away slowly reduces risk. Jaguars are not indiscriminate attackers. They prefer prey that fits established patterns. Humans do not resemble typical prey profiles, and attacks are rare relative to the vast territories jaguars inhabit. Yet rarity does not equate to impossibility. Context matters. Proximity to cubs, scarcity of natural prey, or habituation to human presence can shift thresholds. The river continues its muted flow. Fireflies begin to pulse between trunks. Somewhere downstream, a caiman slides from bank to water with barely a ripple. The jaguar may remain unseen, melting back into shadow once the moment passes. Its decision hinges on energy, risk, and opportunity. It hunts the moment your breathing gives you away, because breath is rhythm, and rhythm signals life under stress. Prey that breathe calmly and move with intention are harder to isolate. Prey that gasp and crash through vegetation declare vulnerability. The Amazon is structured around such thresholds. Each organism carries defenses tuned to its niche. The jaguar's power is not only in muscle and tooth, but in timing. It waits for misalignment between perception and action. The first realization, that you are being watched, is often survivable. The second mistake, turning, running blindly, freezing without context, creates the opening. Falls and cuts amplify noise and scent. Oxygen debt narrows judgment. The forest does not require overt aggression when physiology and terrain collaborate. As twilight deepens, the outlines blur. The rosettes dissolve into pattern. The path along the river remains, etched by generations of hooves and paws. In this environment, survival is as much about managing breath and movement as it is about recognizing predators. The jaguar embodies the apex of this logic, patient, precise, attuned to weakness rather than spectacle. The encounter, even without contact, reveals the broader truth embedded in each previous chapter of the forest's design. The Amazon does not need the first mistake. It waits for the second. At first, the trail looks like a faint crease in the forest floor, a narrow ribbon of cleared earth threading between buttress roots and fallen leaves. It is not a human trail, but an arterial road engineered by insects, a corridor maintained with relentless precision. Along its length, fragments of green move in procession, triangular leaf sections carried aloft by ants whose bodies are small compared to their burdens. In filtered sunlight, the procession resembles a floating mosaic, each piece of foliage advancing in steady rhythm. The trail is not random. It is a lifeline between canopy and colony, between plant and fungus, between energy source and subterranean city. You lower yourself to kneel beside it, perhaps to adjust a bootlace or examine the movement more closely. The ground seems stable, and the ants appear focused on their cargo. Yet the moment weight presses into the trail, the pattern shifts. Leaf-cutter ants of the genera Atta and Acromyrmex operate within a sophisticated social system built on division of labor and chemical communication. Workers range in size from small gardeners tending fungal combs deep underground to large soldiers with powerful mandibles capable of slicing through plant tissue and, if necessary, skin. The disturbance of their highway is interpreted not as a neutral event, but as a potential threat to supply lines. Within seconds, the change becomes visible. Ants carrying leaves drop their cargo and pivot toward the source of vibration. Others emerge from side entrances along the trail, alerted by alarm pheromones released by the first individuals to detect intrusion. The pheromones diffuse rapidly, invisible yet decisive, recruiting nearby workers to converge. The swarm is not chaotic in its own logic. It is structured, a distributed response system calibrated through millions of years of colony-level selection. From your perspective, however, it feels sudden and overwhelming. Boots become platforms. Ants climb with remarkable speed, gripping leather and fabric with hooked tarsi. Hands that brush at them inadvertently provide bridges to sleeves and wrists. Their mandibles, evolved to cut vegetation for fungal cultivation, are sharp and strong. A bite is not venomous in the dramatic sense seen in other insects, but it is forceful enough to break skin. Some species supplement their bite with a formic acid spray, amplifying irritation. The sensation begins as a series of sharp pinches that multiply across ankles and fingers. Each bite is small. Collectively, they create urgency. The second mistake unfolds in response to that urgency. Instinct dictates retreat, but retreat without assessment is blind. You step backward while brushing ants from your legs, eyes fixed downward in an attempt to track the swarm. The forest floor behind you is uneven, a tangle of exposed roots polished slick by humidity. A misplaced step on a root angled at the wrong pitch can twist an ankle. Alternatively, your heel may land on a patch of decaying wood that collapses under pressure, sending you sideways into a shrub whose thorns rake across exposed skin. The ants initiated contact. Gravity and terrain deliver the deeper injury. The ecological context of the swarm reveals why frantic movement is the losing play. Leafcutter colonies can number in the millions. Their survival depends not on individual strength, but on coordinated behavior. The cleared trail reduces obstacles and improves transport efficiency. When that corridor is obstructed, the colony must defend it. Soldiers position themselves along the periphery of disturbance, while smaller workers focus on biting and recruiting. The swarm is targeted, not random. It concentrates on the area of intrusion and dissipates once the threat moves away from the trail. Within the subterranean nest, a different drama unfolds. The leaves harvested above are not consumed directly by the ants. Instead, they serve as substrate for a symbiotic fungus cultivated in carefully maintained gardens. The ants chew leaf fragments into pulp and inoculate them with fungal mycelium, creating a living agricultural system. The fungus produces specialized structures rich in nutrients that feed the colony. This mutualism is ancient and obligate. Neither ant nor fungus survives without the other. The trail you knelt upon is part of a supply chain supporting an underground city whose architecture includes ventilation shafts to regulate temperature and humidity. Thermoregulation in such massive nests is achieved through a combination of structural design and constant maintenance, ensuring that fungal gardens remain within optimal thermal and moisture ranges. As bites accumulate on your hands, the skin may break in small crescents. Blood beads at puncture sites. In a humid forest, open skin invites microbial colonization. The immediate concern, however, is balance. An ankle twisted on a root compromises stability. Pain from the joint radiates upward, altering gait. With ants still crawling and biting, attention fragments. The brain attempts to allocate resources between removing insects and maintaining posture. Coordination falters when sensory input is overloaded. Ants create chaos by exploiting the human aversion to being covered in small moving organisms. The swarm triggers a psychological alarm disproportionate to the physical damage inflicted by individual bites. That alarm drives abrupt, unplanned movements. In evolutionary terms, rapid withdrawal from swarming insects often reduces exposure. In the specific micro-topography of a rainforest floor, however, rapid backward motion without scanning increases the probability of secondary injury. The ant's defense strategy relies on immediacy and numbers, not lethality. They do not need to incapacitate. They need to deter and protect the trail long enough for traffic to resume. Predators of leafcutter ants exist, and they too have adapted to swarm behavior. Certain ant-eating birds time their foraging to army ant raids, exploiting flushed prey. Mammals such as anteaters possess elongated snouts and specialized tongues to harvest ants from nests while minimizing exposure to bites. Their thick skin and dense fur provide partial protection. These predators demonstrate that success against a swarm requires structural or behavioral adaptation, not frantic resistance. Humans, lacking such adaptations, must rely on strategy, stillness, careful retreat, and avoidance of trail intersections. The ant's sensory world is chemical. Trails are marked with pheromones that guide workers with precision. Alarm signals differ from foraging cues, creating layered communication channels. When you sit on a trail, you disrupt not only traffic, but chemical continuity. The colony's response is efficient because it is modular. Each worker responds to local concentrations of pheromone without centralized command. This decentralized intelligence allows rapid scaling of defense. Chaos from your perspective is coherence from theirs. As you attempt to regain composure, slowing movements and stepping deliberately away from the trail's axis reduces the intensity of attack. Ants lose interest once the source of disturbance exits their corridor. Bites diminish in frequency. The immediate crisis passes, but the ankle throbs. Blood from minor cuts mixes with soil. The forest floor's microbial community, essential for decomposition and nutrient cycling, now interacts with open skin. The original contact, kneeling on a trail, was minor. The escalation, blind stepping and frantic brushing, produced the real injury. The broader ecosystem absorbs the disturbance. Leaf fragments once dropped are retrieved. Traffic resumes in steady procession. The colony's fungal gardens continue their quiet growth underground, converting plant biomass into sustenance. The ants' agricultural enterprise influences forest structure by pruning certain plants and redistributing nutrients. Their trails, visible as thin lines across the forest floor, are both highways and ecological signatures. In this environment, swarm behavior is not malevolent, but adaptive. It is a defense scaled to the needs of a superorganism. The losing play is panic, because panic aligns with the ant's objective: rapid removal of the threat from the trail, regardless of collateral damage inflicted by terrain. Measured withdrawal, eyes scanning backward before stepping, hands brushing rather than flailing. These strategies counter chaos with intention. The lesson embedded in the swarm is not about the danger of ants alone, but about how collective behavior interacts with human reflex. Chaos creates the real damage when movement outruns awareness. Night settles differently in tropical lowlands than it does in temperate forests. The air does not cool so much as it thickens, humidity rising from soil that radiates the day's stored heat. Around a small camp clearing, insects pulse toward any source of light, and beyond the edge of the glow, the understory hums with amphibian calls layered in overlapping rhythms. Among them is a deeper, resonant trill that seems to vibrate from the ground itself. Near the path that cuts between tents and cooking area, a large, warty silhouette sits motionless, eyes reflecting a dull amber when the beam of a headlamp crosses them. The marine toad, often known as the cane toad, occupies this threshold between human camp and surrounding ecosystem with quiet persistence. The toad is not subtle in form. Its body is heavy-set, skin thick and glandular, parotoid glands swelling prominently behind each eye like armored saddlebags. These glands are reservoirs of a milky secretion rich in bufotoxins and bufotenins, compounds capable of affecting cardiac and nervous systems in vertebrates. The toad does not deploy these toxins aggressively. They are released when the animal is squeezed or stressed. Its strategy is one of chemical deterrence paired with generalist adaptability. Originally native to parts of Central and South America, the species has been introduced into other regions, where its toxins have reshaped predator-prey dynamics by poisoning animals that attempt to consume it. You move the toad from the path not out of curiosity, but convenience. Its bulk blocks the narrow walkway between camp gear and cooking area. The skin feels cool and slightly damp beneath your hands, textured with tubercles that exude faint moisture. The toad inflates slightly in response, a defensive posture that increases apparent size. As fingers press near the parotoid glands, a thin smear of toxin may coat the skin. The secretion is not explosive or dramatic. It is subtle, sticky, and easily overlooked in dim light. The toad hops away into leaf litter, disappearing with surprising agility for its size. The ecosystem around the camp continues its nocturnal negotiations. Beetles navigate toward food scraps. Geckos hunt moths drawn to lantern glow. Small mammals skirt the perimeter, cautious but curious. The marine toad, opportunistic and omnivorous, feeds on insects attracted to light and on discarded organic matter. Its success in disturbed habitats stems from dietary flexibility and reproductive capacity. Females can lay thousands of eggs in shallow water bodies, and the tadpoles develop rapidly in warm, nutrient-rich pools. The species thrives where human presence inadvertently creates new niches. the toxin on your hands remains invisible. Under the heat of cooking fires and the exertion of camp tasks, sweat forms along the brow and upper lip. The reflex to wipe is as automatic here as in any humid environment. Fingers brush across skin, transferring trace amounts of toxin to mucous membranes. Alternatively, you reach for food, adjust a cigarette, or sip from a cup without thorough washing. The mouth becomes the first true point of contact for the chemical defense that was meant for a predator's jaws. Burning begins along the lips and inside the mouth, a bitter, metallic taste blooming across the tongue. The buccal mucosa absorbs compounds more readily than intact external skin. Nausea follows as the body recognizes a foreign substance. Bufotoxins can influence cardiac rhythm and cause gastrointestinal distress when ingested in sufficient quantities, though small incidental exposures more commonly produce irritation, salivation, and discomfort. Dizziness may emerge not solely from systemic toxicity, but from the combination of stress response and mild hypertension triggered by vagal reflexes associated with nausea. The critical shift occurs not in the chemistry alone, but in coordination. The vestibular system in the inner ear integrates with visual cues and proprioceptive feedback from muscles to maintain balance. When nausea and dizziness disrupt this integration, posture wavers. In a forest camp environment, the ground is rarely even. Roots protrude, cookware lies near footpaths, and embers from a fire glow faintly. A moment of imbalance can lead to a stumble over a tent stake or a fall against stacked equipment. The toxin, while unpleasant, is not necessarily catastrophic. Impaired coordination in a cluttered environment is. The theme that emerges is one of hands as hazard. The hands are tools of interaction, lifting, moving, cooking, adjusting gear. In handling the toad, they became vectors. Washing with insufficient water or without soap leaves residues in skin creases and beneath fingernails. Sweat reactivates and spreads these residues, particularly in the tropics where evaporation is limited. Each wipe of the brow, each adjustment of glasses or brushing of hair reintroduces irritants to sensitive tissues. The re-triggering effect can create a cycle in which irritation seems to flare unpredictably, though the mechanism is simply repeated transfer. From the toad's perspective, the toxin is an evolutionary answer to predation. Many native predators in its original range have developed behavioral avoidance or partial physiological tolerance. In regions where the toad is invasive, predators such as certain snakes, marsupials, or carnivorous mammals may lack such adaptations and suffer lethal consequences after ingestion. This imbalance illustrates how chemical defenses can ripple through ecosystems, altering predator populations and cascading into shifts in prey abundance. The toad's skin glands represent a powerful survival tool that, when introduced into new ecological contexts, becomes a disruptive force. Thermoregulation also influences the dynamics of exposure. Amphibians rely on moist skin for cutaneous respiration and water balance. In humid environments, the toad's skin remains pliable and active in secretion. For humans, the same humidity compromises evaporative cooling and keeps skin damp, increasing permeability and the persistence of residues. The shared dependence on moisture creates an interface where chemical exchange is more likely. The toad's glands are most effective when pressed. Human sweat ensures that what is pressed does not dry quickly. As nausea builds, attention narrows. The mind focuses on internal discomfort rather than external hazards. Peripheral vision may dim slightly with dizziness, and reflexes slow. In this state, decisions are reactive rather than measured. A quick attempt to move away from campfire heat may result in stepping onto unstable ground. A hurried walk toward water for rinsing may ignore the uneven slope of a stream bank. The toxin itself did not incapacitate entirely. It disrupted equilibrium just enough to increase risk. Meanwhile, the marine toad resumes its routine. It settles beneath a shrub, throat pulsing as it calls intermittently to attract mates during breeding season. Its large eyes track movement of insects drawn to residual light. The parotoid glands, having released only a fraction of their contents, remain full enough to deter the next predator. The toad does not pursue conflict. It relies on contact-based defense, trusting that most large animals will learn to avoid it after a single unpleasant experience. In the broader ecosystem, amphibians serve as both predators and prey, regulating insect populations and providing food for birds, reptiles, and mammals. Their permeable skin makes them sensitive indicators of environmental change, vulnerable to pollutants and habitat shifts. The marine toad's robustness and adaptability stand in contrast to many amphibians experiencing global declines. Its success, however, is entwined with chemical potency that can unbalance communities where it is not native. As the symptoms gradually ease, mouth rinsed thoroughly, hands washed with soap, fresh water used to clear sweat, the immediate crisis recedes. Yet the pattern remains instructive. Handling a chemically defended organism transformed hands into conduits. Sweat and routine gestures amplified exposure. Impaired coordination, not raw toxicity, posed the greatest danger in a terrain defined by obstacles and heat. The forest at night remains dense and indifferent, layered with calls and rustling movements. The marine toad sits within it, a heavy-bodied sentinel armed not with aggression but with chemistry. The escalation that followed was not an attack, but a cascade born of transfer, moisture, and the simple human habit of wiping sweat from a brow. The air above the forest floor appears empty until you stand still long enough to feel it. In the humid understory, where shade holds the day's moisture in suspension, the atmosphere is not inert but inhabited. Mosquitoes drift in loose spirals, nearly invisible against the green lattice of leaves and filtered light. They do not move randomly. Carbon dioxide plumes from exhaled breath rise in faint expanding columns. Lactic acid and other volatile compounds seep from skin. Heat radiates from exposed flesh. To a mosquito, these are coordinates. The female, seeking a blood meal to mature her eggs, orients along chemical gradients and infrared signatures with extraordinary precision. The first bite lands near the neck, just below the ear, where skin is thin and vascular. Another settles on the upper eyelid, a location chosen not by malice but by opportunity. Blood vessels lie close to the surface in these regions, and the warmth is constant. The mosquito inserts its proboscis not as a single needle, but as a bundle of fine stillets that slide between skin cells. Saliva containing anticoagulants and immunomodulatory proteins is injected to prevent clotting and to dampen immediate detection. The withdrawal is almost imperceptible. It is the body's response that announces the intrusion. Within minutes, histamine floods the site. Capillaries dilate. Fluid accumulates in surrounding tissue. The itch is intense and specific, a signal that demands attention. Around the eyelid, the swelling is disproportionate to the size of the wound because the tissue is loose and richly supplied with blood vessels. The thin dermis of the eyelid accommodates fluid easily, creating puffiness that can partially close the eye. Vision narrows not because of direct injury to the globe, but because the mechanical aperture through which light enters is compromised. The reflex to scratch is immediate and deeply rooted in neurobiology. Itching activates neural circuits overlapping with pain pathways, and scratching provides temporary relief by stimulating competing sensory inputs. Fingernails rake across the bite site, abrading the surface. In a forest environment where sweat, dust, and microbial particles cling to skin, this abrasion opens a portal. Sweat carries salts and organic compounds that can irritate further when driven into microtears. Grime from hands, leaf fragments, soil particles, fungal spores adheres to raw skin. The result is not a single clean puncture, but a patch of inflamed, compromised tissue. Eyelid swelling carries particular consequences for navigation. Depth perception depends on binocular vision and subtle cues such as shadow gradients and motion parallax. When one eyelid droops or tears blur the visual field, the brain receives asymmetrical input. Even slight discrepancies can distort spatial judgment in cluttered terrain. The forest floor is a study in irregularity. Roots arc unpredictably, fallen branches conceal holes, and lianas hang at varying heights. Peripheral vision detects movement and helps maintain balance by providing reference points. Swelling that narrows the palpebral fissure reduces that peripheral field. The world becomes a tunnel edged in softness. Mosquito ecology is entwined with water. Eggs are laid in stagnant pools, tree holes, or slow-moving streams. Larvae hang beneath the surface, breathing through siphons while feeding on organic detritus and microorganisms. The presence of mosquitoes signals nearby water bodies, which in turn support amphibians, insects, and a cascade of aquatic life. Predators such as dragonfly nymphs and small fish regulate larval populations, yet the sheer reproductive capacity of mosquitoes ensures persistence. Their life cycle is rapid, tuned to exploit ephemeral water sources created by rainfall. In tropical forests, breeding sites are abundant and transient, scattered across bromeliad axials, hoofprints filled with rain, and the shallow margins of streams. As bites accumulate around the eyes and neck, attention fragments. The neck, rich in sensory nerves and exposed to airflow, becomes another focal point of irritation. Swelling there may not impair vision directly, but can alter posture as the head tilts to avoid contact with clothing. Repeated scratching diverts cognitive resources from scanning terrain. The brain's attentional network has finite capacity. Persistent itch occupies bandwidth that would otherwise process environmental cues. Walking becomes less deliberate. Foot placement shifts from careful to automatic, increasing the likelihood of missteps. Mosquito saliva is not merely an irritant. It is a complex pharmacological mixture evolved to facilitate blood feeding. In some species, pathogens exploit this pathway, using the mosquito as a vector to move between hosts. While not every bite carries disease, the evolutionary interplay between mosquito, pathogen, and host has shaped immune responses across vertebrates. The swelling and itch are part of a defensive reaction designed to expel and isolate foreign material. Ironically, this protective response contributes to the sensory disruption that undermines safe movement in challenging terrain. The act of scratching until skin opens introduces another layer of risk. Broken skin in a humid environment is vulnerable to secondary infection. Bacteria common in soil and on human skin can colonize small wounds, leading to localized cellulitis if conditions allow. The inflammatory response intensifies, increasing swelling and tenderness. Around the eye, even minor infection can exacerbate puffiness, further narrowing vision. The jungle doesn't need to inflict a major wound. A small lesion, multiplied by environment and behavior, can escalate. As you walk, the combination of narrowed vision, distraction, and altered posture compounds. A route that would have been easily stepped over becomes a trip hazard. A low branch grazes the forehead because the peripheral cue was missed. A slip on damp leaf litter sends a jolt through the ankle. The fall itself may be minor, but it adds to the accumulation of strain and abrasion. Mosquitoes, individually insignificant in mass, collectively shape behavior through relentless attention theft. In the canopy above, birds feed on adult mosquitoes, integrating them into the food web. Bats emerge at dusk, sweeping through air columns with echolocation pulses, harvesting insects in mid-flight. Spiders stretch webs across narrow clearings, intercepting the unwary. Mosquitoes are prey as much as they are parasites, linking aquatic and terrestrial systems. Their persistence despite predation underscores a life strategy built on abundance and rapid turnover rather than individual survival. Thermoregulation in humans during exertion in humid forests is compromised by high ambient moisture. Sweat lingers, increasing skin hydration and susceptibility to irritation. The same humidity that nurtures mosquito breeding also amplifies the sensory impact of their bites. Swollen eyelids trap moisture against lashes, creating a microenvironment where tears and sweat mix, sustaining itch. Repeated wiping redistributes irritants and potentially additional bites to new areas. The jungle wins not through dramatic confrontation, but through incremental erosion of focus. A mosquito bite is small. Its physiological footprint is minor compared to that of larger predators or venomous animals. Yet its strategic placement around eyes and neck targets sensory gateways. Vision and attention are foundational to safe movement in complex habitats. When those are compromised, even temporarily, the probability of error rises. As the swelling gradually subsides and the itch fades, clarity returns. The forest regains depth and texture. The episode illustrates how minute organisms exploit universal vulnerabilities: thin skin, exposed vessels, reflexive scratching. The mosquito does not seek to cause a fall. It seeks a blood meal to provision eggs. The cascade that follows is collateral, born of human physiology interacting with terrain. In the interplay between insect and environment, the smallest intrusion can ripple outward, reshaping behavior and altering risk. In the humid green labyrinth, attention is as vital as footing, and even a small bite near the eye can tilt the balance. The forest after rain becomes a chamber of condensation, every surface sheened with moisture that blurs the boundary between air and leaf. Bromeliads cradle small reservoirs in their cupped centers. Tree trunks sweat along their ridges, and the understory hums with the low-frequency pulse of insects resuming activity after the downpour. In this saturated world, color does not hide. It declares. On a low leaf a few inches above the soil, a poison dart frog sits in still composure, its skin a luminous mosaic of electric blue and black or gold and obsidian, depending on the species. The brightness is not camouflage, but advertisement, a signal refined through evolutionary time to broadcast a simple message: do not touch. The frog does not leap away immediately. Many dendrobatid frogs rely on confidence rather than concealment. Their toxins, sequestered from the arthropods they consume, particularly certain ants, mites, and beetles are stored in granular glands within the skin. These alkaloid compounds, including batrachotoxins in some species, interfere with sodium channels in nerve cells, disrupting electrical signaling. In predators lacking resistance, ingestion or significant contact can lead to paralysis or cardiac failure. The frog itself is immune, its physiology adapted to tolerate compounds that would overwhelm other vertebrates. Its stillness is strategic. Movement attracts attention, while warning coloration coupled with toxicity creates an honest signal within the ecosystem. Your hand brushes the leaf on which the frog recently rested. The frog has already hopped to a neighboring perch, leaving behind a faint trace of moisture where its ventral surface contacted the plant. In a dry environment, such residue might evaporate quickly, but here evaporation is slow. Humidity preserves microfilms of secretions on leaf surfaces. The toxins are not actively sprayed or projected. They exist in skin secretions that can be transferred passively. The contact feels unremarkable. The leaf is cool and slick, no different from dozens of others encountered moments before. The risk lies not in the initial touch, but in what follows. Sweat forms along your temples and upper lip. In high humidity, the body struggles to regulate temperature through evaporation. Sweat accumulates rather than dissipating, forming a thin saline layer that increases the permeability of skin and soft tissues. The instinct to wipe is immediate. Fingers, still damp from contact with the leaf, move toward the face to clear sweat from the brow or adjust the corner of the mouth. The frog did not attack. It did not need to. Transfer occurs through routine behavior. The mucous membranes of the eyes, nose, and mouth are not armored like the outer epidermis. They are designed for exchange of light, of air, of taste, and are richly supplied with blood vessels and nerve endings. When frog toxins contact these tissues, irritation begins rapidly. A burning sensation may flare along the lip or at the edge of the nostril. If a small cut on the finger provides a direct entry point, localized tingling can intensify as compounds interact with nerve endings. Panic breathing may follow, not necessarily because of systemic toxicity, but because the sensation around the mouth or throat triggers a reflexive fear of airway compromise. In most casual contact scenarios with poison dart frogs, the amount of toxin transferred through intact skin is minimal and unlikely to cause severe systemic effects. The danger in this context is less about lethality and more about disruption. The burning irritation around the eyes produces tearing. Vision blurs as the tear film destabilizes and eyelids blink repeatedly in an attempt to clear the sensation. Around the mouth, tingling or numbness alters the perception of breathing. The brain, wired to respond aggressively to any signal suggesting airway threat, elevates heart rate and respiratory rate. Hyperventilation follows, with all the attendant consequences of reduced carbon dioxide levels and dizziness. The real hazard is the amplification created by humidity and sweat. Moisture facilitates transfer, spreading compounds across larger areas of skin and into creases and microabrasions. The rainforest's constant dampness means that residues persist longer on surfaces. A frog that moved across a cluster of leaves may leave trace alkaloids on multiple contact points. Hands that brush one leaf may collect residue and deposit it onto another object, gear, a water bottle, a strap, creating secondary vectors. In a laboratory, toxins are measured in micrograms. In the forest, Their distribution is guided by capillary action along water films and by the simple mechanics of touch. Ecologically, poison dart frogs are woven into a network of chemical exchanges. Their toxins originate from diet. When raised in captivity on non-toxic food sources, many species lose their chemical defenses. This dependency highlights a trophic cascade in which plant chemistry influences insect chemistry, which in turn influences amphibian toxicity. The frog's bright coloration participates in Mullerian mimicry rings, where multiple toxic species converge on similar color patterns to reinforce predator learning. Birds and snakes that attempt predation and experience illness may avoid similarly colored frogs in the future. The ecosystem remembers through behavior. The frog itself is small, often only a few centimeters in length, yet its reproductive strategies reveal complexity beyond its size. Some species transport tadpoles individually to water-filled bromeliad axils, climbing vertical trunks with adhesive toe pads that function through a combination of surface tension and microscopic structures. In certain species, the female returns periodically to deposit unfertilized eggs as food for developing larvae, a form of parental investment rare among amphibians. These behaviors occur in the same humid microhabitats where toxins are most stable. The frog's life cycle is embedded in moisture. As irritation spreads across the face, clarity of thought narrows. The forest, once a layered tapestry of textures and colors, becomes a field of obstacles to navigate quickly. A misjudged step on slick clay can twist an ankle. A stumble into low branches can scrape skin already compromised by minor cuts. The escalation is not dramatic, but cumulative. One compromised sense feeds into another. Vision blurred by tearing alters depth perception. Rapid breathing induces lightheadedness. Decision-making shifts from deliberate scanning to urgent retreat. The frog remains perched nearby, throat pulsing gently as it calls with a high, insect-like trill to attract a mate. Its call carries through the damp air, a sonic thread weaving through the understory. It has not engaged in aggression. It has simply occupied its niche, advertising toxicity and relying on predators' capacity to learn. The transfer that occurred was incidental, a byproduct of proximity and humidity. In evolutionary terms, the frog's strategy is efficient. It invests in chemical defense and conspicuous coloration, reducing the need for flight. The burden of miscalculation falls on the organism that ignores the signal. In humid forests, moisture is both lifeline and vector. It supports amphibian respiration through permeable skin and sustains plant transpiration cycles. It also preserves chemical residues and enhances the mobility of compounds across surfaces. Human skin, when wet, becomes more permeable, particularly where friction has created microtears. Sweat, while essential for thermoregulation, becomes a medium that spreads irritants. The interplay between environmental humidity and physiological response defines the boundary between harmless contact and disruptive exposure. As the burning sensation gradually subsides and breathing steadies, the lesson embedded in the encounter clarifies. The frog did not leap to defend itself. It did not bite or chase. Its defense was passive yet potent, dependent on a network of moisture and touch. The most vulnerable points, the eyes, mouth, small cuts, are not inherently weak but designed for exchange with the environment. In a rainforest saturated with chemical signals, that exchange must be navigated carefully. The ecosystem continues its intricate choreography. Ants march along leaf edges. A snake glides through leaf litter, perhaps immune to certain frog toxins. A bird calls from the canopy, adjusting its foraging route based on learned associations of color and taste. The poisoned dart frog remains a bright punctuation mark against green, a living testament to the power of chemistry in shaping behavior. The true danger lies not in overt aggression, but in the quiet transfer facilitated by humidity, sweat, and reflexive touch. In this environment, self-poisoning through panic is a more likely escalation than deliberate attack. The forest does not always strike. Sometimes it simply waits for hands to move from leaf to face. The log looks harmless in the filtered light of the understory, its bark softened by humidity, its surface layered with moss and fungal threads that glow faintly green where sun shafts find them. In tropical forests and warm, temperate regions alike, fallen wood is not debris but infrastructure, a vertical apartment complex for beetle larvae, termites, spiders, amphibians, and predators that hunt them. When a hand slides beneath bark to lift or steady it, the gesture is efficient and automatic, guided by habit rather than inspection. Beneath that bark, pressed flat against damp cellulose, a centipede lies coiled along the grain like a living hinge. Its body, segmented and lacquered in reddish-brown, is built for these narrow spaces. The contact is sudden. The bite lands before the shape of the animal registers in the mind. Scolopendra species are not passive scavengers. They are active nocturnal hunters, equipped with a pair of modified front legs known as forcipules. These appendages curve forward like hooked forceps, tipped with venom glands that deliver a rapid injection when they close. The bite does not tear in the way mammalian teeth do. It clamps and injects, releasing a venom cocktail containing proteins, peptides, and enzymes that affect nerve cells, muscle fibers, and local blood vessels. Pain blooms almost instantly, sharp and electric, followed by a deep burning that radiates along the limb. Swelling begins within minutes as inflammatory mediators flood the tissue. The hand, so recently an instrument of control, becomes the center of neurological noise. The centipede's position under bark is not incidental. These arthropods require moisture to avoid desiccation, and the microclimate beneath logs, stones, boots, or bedding offers stable humidity and temperature. Thermoregulation in centipedes is behavioral. They cannot generate internal heat, so they select environments that buffer them against extremes. By day, they remain hidden in cool, damp refuges, emerging at night to hunt insects, spiders, and occasionally small vertebrates such as lizards or nestling rodents. Their antennae sweep constantly, sampling chemical cues and vibrations in the substrate. To a centipede, the underside of a boot left on the forest floor or the fold of bedding in a field camp is not human gear. It is a cave with favorable moisture and prey potential. When the bite lands, the reflex is to recoil. Muscles contract sharply, and the hand jerks away in an uncoordinated arc. If the other hand holds a tool, it may be dropped. If balance depends on the lifted log, that support collapses. The forest floor, uneven and layered with splintered wood, thorns, and sharp stone fragments, is unforgiving. A fall into debris produces secondary injuries, cuts across the palm, punctures along the forearm, perhaps a scraped knee driven into soil rich with bacteria and fungal spores. The initial bite, painful but typically not life-threatening in healthy adults, becomes the trigger for a chain reaction. The environment compounds the error. Blind shaking is a common escalation. Without visual confirmation of where the centipede has gone, the hand flails, potentially striking nearby surfaces or driving the animal against skin for additional bites. Scolopendra are capable of multiple strikes in rapid succession, especially when pinned. Their bodies are flexible, able to twist and anchor with posterior legs, while the front segments attack. In the darkness, under bark, or inside a boot, this flexibility is an advantage refined over millions of years. The centipede's exoskeleton protects against compression, and its many legs distribute force across the substrate. It is not aggressive in a strategic sense, it is defensive in tight quarters. The new wounds from a fall introduce a different ecological narrative. Tropical and subtropical soils teem with microorganisms adapted to warm, moist conditions. Bacteria such as Staphylococcus and Streptococcus species, along with environmental organisms and fungi, inhabit the leaf litter. A puncture or abrasion contaminated with soil becomes a portal. In this context, the centipede's venom is only one factor in a broader risk landscape. The immune system must now manage both envenomation and potential infection. Swelling from the bite may restrict finger movement, reducing dexterity. With one hand compromised, every subsequent task, climbing over roots, lifting gear, steadying oneself on slick surfaces, becomes more hazardous. Where do bites most often occur? Field observations and medical case reports indicate patterns tied to human behavior. Boots left outdoors overnight provide dark, humid cavities attractive to centipedes seeking refuge. Sliding a bare foot into such footwear without inspection creates a perfect setup. Bedding placed directly on ground or near walls in tropical dwellings can harbor centipedes that wander in search of prey. Logs and stacked firewood offer layered shelter. Even backpacks and rolled clothing left in damp conditions can become temporary hideouts. The common thread is blind contact with concealed spaces. The centipede does not pursue open confrontation. It capitalizes on enclosed environments where escape routes are limited. In ecological terms, Scolopendra occupy the role of mid-level predators. They regulate populations of insects and other arthropods, influencing decomposition rates and nutrient cycling. By preying on termites and beetle larvae, they indirectly affect how quickly wood breaks down. Some larger species can overpower small vertebrates, injecting venom that disrupts neuromuscular transmission. The venom's composition varies among species, reflecting local prey assemblages and evolutionary pressures. In island ecosystems, where certain vertebrate prey are abundant and mammalian predators scarce, centipedes may grow larger and adopt more aggressive hunting behaviors. Their physiology is tuned to rapid immobilization of prey in confined spaces. As the bitten hand throbs, vascular changes amplify the sensation. Local blood vessels dilate, allowing immune cells to access damaged tissue. Edema compresses surrounding nerves, intensifying pain. Movement becomes both necessary and dangerous. The forest demands constant interaction, grasping vines, pushing foliage aside, stepping over roots. With one hand disabled, reliance shifts to the other, increasing strain and the likelihood of imbalance. Fatigue accumulates faster. Small missteps, once trivial, become consequential. A stumble on a slick root may twist an ankle. A failed grip on a branch may result in a deeper fall. Injuries accumulate not through a single dramatic event, but through a series of compromised adjustments. The centipede, meanwhile, retreats. Its metabolic rate is relatively low compared to endothermic animals, but its predatory bursts are efficient. After a defensive bite, it seeks another crevice, guided by humidity gradients and the chemical absence of disturbance. Its segmented body, each pair of legs operating in coordinated waves, allows it to navigate uneven terrain with surprising speed. In some species, the final pair of legs are elongated and sensitive, used to sense threats from behind. These sensory adaptations enable rapid assessment of escape routes in cluttered habitats. The animal's survival depends on minimizing exposure to large predators, including humans. There is a subtle irony in how the setup unfolds. The human hand, an organ of manipulation and curiosity, reaches into concealed spaces to move, inspect, or retrieve. In doing so, it intersects with a species whose entire evolutionary trajectory favors hidden occupation of those same spaces. Blind grabbing is not merely a lapse in caution, it is a mismatch between two survival strategies. One relies on tactile exploration and assumption of control. The other relies on concealment and immediate defense. Over time, the swelling subsides and tissue repair begins. Most centipede bites resolve without lasting damage, though the memory of pain lingers. The forest, indifferent to individual encounters, continues its layered processes. Fungi digest lignin in fallen logs. Ants patrol trails scented with pheromones. Amphibians hunt at dusk along the same damp corridors where centipedes roam. Each organism occupies a niche shaped by moisture, temperature, and available prey. The centipede's role as both predator and defensive occupant of microhabitats contributes to the stability of this complex web. In this environment, vision is often limited by foliage and shadow. Tactile exploration becomes necessary, yet it carries inherent risk. The lesson embedded in the bite is not solely about venom potency. It is about the architecture of concealed ecosystems. Boots, bedding, logs, and gear are extensions of the landscape once placed within it. They are absorbed into the forest's network of shelters and hunting grounds. Blind contact collapses the boundary between human intention and arthropod refuge. When one hand falters under pain and swelling, the cascade of risk expands outward, touching balance, movement, and judgment. The centipede does not need to incapacitate entirely. It needs only to disrupt. In a terrain defined by uneven surfaces and hidden edges, even minor disruption can propagate into accumulating injury. The forest floor at dusk holds a particular stillness that is not silence but compression, as if the day's heat and motion have been folded into the soil. A shallow burrow opens at the base of a root buttress, rimmed with silk, that blends seamlessly with leaf litter. The architecture is subtle. A thin lining of webbing stabilizes loose soil grains, creating a tunnel just wide enough for a large-bodied spider to turn and brace. From within that aperture, a tarantula waits, its body low, legs splayed in a posture that is neither aggressive nor relaxed, but ready. In the fading light, the hairs along its abdomen catch faint gold from the last slant of sun filtering through canopy gaps. These hairs are not ornamental. They are loaded. When a disturbance approaches, footfall vibrations transmitted through soil, the shadow of a larger animal passing overhead, the displacement of air, the tarantula does not immediately bite. Biting is metabolically expensive and mechanically risky. It requires close contact. Instead, many New World tarantulas deploy a more economical defense. With a rapid scraping motion of their hind legs against the abdomen, they release a cloud of specialized urticating hairs into the air. These hairs are microscopic barbed structures, each tipped and serrated in a way that encourages penetration into soft tissue. To the human eye, the motion may appear as a slight flick, a blur of legs. To the surrounding environment, it is a dispersal event. The hairs drift on air currents, settling onto skin, clothing, and exposed surfaces. If you are close enough to peer into the burrow or to brush aside vegetation without noticing the spider's posture, you may not register the flick until the sensation begins. At first, it is subtle, a prickling across the back of the hand or along the forearm. Then the itch intensifies, accompanied by a sharp irritation that seems to migrate as you move. The reflex is immediate and universal. Brush it off, rub it away, blow on the skin to clear invisible debris. Yet the very structure of these hairs ensures that friction drives them deeper. Under magnification, each urticating hair resembles a spear with backward-facing barbs. When they contact mammalian skin, they embed in the outer layers of the epidermis. Rubbing creates shear forces that break the hairs and force fragments into microabrasions. Blowing on the hands disperses loose hairs into the air column around your face. The cornea and conjunctiva, delicate and richly innervated tissues designed for optical clarity, are particularly vulnerable. A single hair lodged in the conjunctival sac can trigger intense tearing and photophobia. Multiple hairs produce a burning sensation that competes with vision itself. The persistence of irritation is rooted in immunology as much as mechanics. The embedded hairs are foreign bodies. Their barbs prevent easy expulsion, and their surfaces may carry small amounts of irritating compounds. The body responds with localized inflammation. Mast cells release histamine, increasing vascular permeability and recruiting immune cells to the site. In the skin, this manifests as redness, swelling, and an itch that can last hours or days. In the eyes, inflammation causes redness, tearing, and blurred vision as the tear film becomes unstable. The cornea's transparency depends on precise hydration and cellular organization. Disruption introduces haze. As vision blurs, spatial awareness degrades. The forest floor, already a mosaic of uneven surfaces, becomes unpredictable. Roots protrude at ankle height, leaves conceal small depressions, and damp clay patches shift under weight. Depth perception relies on binocular clarity and subtle contrast cues filtered through the canopy. When one eye waters excessively or both eyes struggle to focus, the brain receives conflicting information about terrain. A misjudged step on a slick route can send the body forward. Hands reach instinctively to break the fall, but if those hands are already irritated and partially numb from scratching, grip strength falters. A fall may drive knees into sharp sticks or palms into grit that grinds into already inflamed skin. The tarantula's defensive strategy is elegant in its economy. It does not need to overpower a large predator. It needs to create enough discomfort and sensory disruption to discourage further intrusion. Urticating hairs are renewable to a degree, regrown with successive molts. For a ground-dwelling spider that cannot outrun birds or small mammals in open terrain, the ability to deploy a persistent irritant at distance confers survival advantage. Some species can aim their hair flicks with surprising accuracy, orienting their abdomen toward the threat. Others rely on close-range dispersal within confined spaces such as burrows, where air currents are minimal and contact is likely. Ecologically, tarantulas occupy the role of nocturnal ambush predators. They hunt insects, small reptiles, amphibians, and occasionally small mammals. Their venom, delivered through chelicerae, is adapted primarily for subduing arthropod prey, though it can deter vertebrates. Yet the hairs, not the venom, are often the first line of defense against large animals. In some ecosystems, tarantulas share burrow systems with small frogs that benefit from the spider's protection against predators while providing the spider with parasite removal. These symbiotic relationships underscore the spider's integration into broader community dynamics. The burrow is not merely a hole in the ground, it is a microhabitat supporting multiple species. Thermoregulation also shapes tarantula behavior. As ectotherms, they depend on environmental heat to regulate metabolic processes. During the day, many remain in burrows where temperature and humidity are stable. At night, when temperatures drop and humidity rises, they emerge to hunt. The timing reduces water loss and exposure to diurnal predators. When a human hand intrudes during daylight hours, it often intersects with a spider at rest, already oriented toward defense within a confined space. The flick of hairs is a response calibrated for this narrow, humid chamber. Panic rubbing multiplies the problem not only by embedding hairs deeper, but by spreading them across new surfaces. Hands that brush the forearm may carry hairs to the neck or cheeks. Fingers that wipe sweat from the brow deposit irritants near the eyelids. Each transfer expands the affected area. The sensation becomes diffuse, harder to localize, and therefore more frustrating. In response, rubbing intensifies, creating a feedback loop between irritation and mechanical force. The more one attempts to clear the skin through friction, the more deeply the barbed structures lodge. In rare cases, ocular exposure to tarantula hairs can lead to more serious complications such as keratitis if hairs penetrate the cornea. The eye's immune response, while protective, can produce additional swelling that compromises visual acuity. In a dense forest environment where orientation depends on clear sightlines through layers of vegetation, even temporary visual impairment carries risk. The forest is three-dimensional. Hazards are not only underfoot, but at head height and above. A misjudged duck under a branch can result in a facial scrape or scalp laceration. A stumble into a thorny shrub introduces new punctures that invite microbial colonization. Meanwhile, the tarantula retreats into its burrow, abdomen lowered, legs braced. The hairs it has released settle into leaf litter, becoming indistinguishable from the countless plant fibers and fungal threads that carpet the ground. The spider's metabolic expenditure is minimal compared to the potential cost of a bite delivered to a large animal. Its survival depends on discouragement rather than dominance. In evolutionary terms, the strategy is conservative and efficient. The broader ecosystem continues its quiet negotiations. Moths flutter in the growing darkness, drawn to faint glimmers of reflected light. Beetles navigate along scent trails left by decaying fruit. A small mammal pauses near the burrow entrance, nose twitching, perhaps remembering a previous encounter with airborne irritants. Predator-prey interactions are shaped as much by memory and avoidance as by direct confrontation. The tarantula's hairs imprint lessons across species boundaries. As tearing subsides and inflammation gradually stabilizes, the incident reveals a principle embedded in many forest defenses. Sensory disruption can be as effective as physical injury. Vision, touch, and balance are interconnected systems. When irritation persists, attention narrows. Decision-making becomes reactive rather than deliberate. The forest rewards patience and measured movement. Panic, particularly expressed through rubbing and blind-clearing gestures, transforms a manageable irritant into a cascade of impairments. In this environment, the smallest structures, microscopic hairs lighter than dust, can alter the trajectory of a body moving through complex terrain. The tarantula does not chase, does not roar, does not need to wound deeply. It releases a cloud and waits for physiology to do the rest. The lesson carried in the itch and blur is not merely about discomfort, it is about the fragility of perception when confronted with biological design honed for survival in shadows and soil. The forest corridor narrows not because the path disappears, but because the vegetation thickens into a layered wall of leaves, vines, and suspended debris that has been assembling itself for decades. In the understory of a humid tropical rainforest, light arrives fractured and filtered, and every surface holds moisture long after the last rain has passed. Broad leaves overlap like shingles, directing runoff down their central veins, forming living gutters that guide water, insects and spores toward the forest floor. When you move through this corridor, you are not simply brushing plants aside. You are entering a dense, vertical ecosystem in which every leaf is both habitat and trap. Your forearm grazes one of these leaves, and the contact feels insignificant at first. A soft resistance, a texture slightly rougher than the surrounding foliage. Then the skin begins to flare. The sensation does not come from a bite in the traditional sense. It comes from a field of microscopic structures designed for defense long before you arrived. Many venomous caterpillars, including species in the genus Lonomia, carry dense arrays of urticating spines that are hollow or barbed and connected to glands containing venom. These spines are not ornamental. They are evolutionary compromises between mobility and vulnerability. A caterpillar cannot outrun a predator, cannot strike with speed, and cannot rely on camouflage alone in a forest where countless eyes search every surface for protein. Instead, it becomes a living minefield. Each spine is a hypodermic needle scaled down to a fraction of a millimeter, fragile enough to snap on contact and strong enough to embed in mammalian skin. When your arm brushes the leaf, dozens of these spines detach and penetrate the outer layer of your skin. The epidermis, designed to block microbes and retain moisture, is not designed to repel barbed silica-like shafts tipped with venom. As the spines break, they release a complex cocktail of bioactive compounds that interact with pain receptors and inflammatory pathways. The skin lights up not metaphorically, but physiologically. Nociceptors, specialized sensory neurons, fire in response to mechanical damage and chemical irritation, sending rapid signals toward the spinal cord and brain. Blood vessels dilate. Local immune cells release histamines and cytokines. The area reddens and swells as fluid shifts into the tissue. What feels like fire is a carefully orchestrated inflammatory cascade, a defensive reflex that evolved to isolate and repair damage. The second mistake arrives almost automatically. The body interprets the pain as a surface irritant, something to be brushed away or scratched out. Your hand moves to rub the area, and friction increases. Under magnification, this friction is catastrophic. The spines that did not fully embed are driven deeper. Those that fractured near the surface are dragged laterally, creating micro tears in the skin. Sweat already forming in the humid air as your body attempts thermoregulation through evaporative cooling, mixes with venom residues and carries them across adjacent patches of skin. The sleeve that wipes across your forearm does not clean, it collects. The fabric's fibers catch detached spines like Velcro, storing them invisibly. As you move again through the corridor, your clothing brushes your neck, your wrist, your side. Each contact becomes a secondary exposure. The shirt is no longer neutral fabric. It is a reservoir of microscopic barbs, reactivated with every shift in posture. The irritation expands from a single patch into a widening burn zone, not because the caterpillar pursued you, but because your own defensive movements redistributed its defenses. In this way, the caterpillar's survival strategy extends beyond the initial contact. It leverages the predictable reactions of larger animals, scratching, sweating, wiping, to amplify its reach. Evolution has selected for structures that exploit mammalian reflexes. In some species, the venom does more than cause localized pain. Certain Lonomia caterpillars produce toxins capable of interfering with blood-clotting pathways in humans, leading in rare but severe cases to hemorrhagic complications. These toxins evolved not specifically to harm humans, but to deter or incapacitate small vertebrate predators. The biochemical targets, enzymes in the coagulation cascade, are ancient and conserved across many vertebrates. A bird that attempts to swallow such a caterpillar may experience internal bleeding or prolonged inflammation, reducing its future foraging efficiency. A mammal that brushes against a colony and suffers intense pain may avoid similar foliage in the future. The cost of predation increases. The caterpillar's relatively simple body, slow and leaf-bound, survives by making itself disproportionately expensive to attack. The forest context deepens the story. Venomous caterpillars often cluster along leaf veins or rest in tight groups that mimic fungal growths or bark textures. Their coloration can be deceptive. Some blend into the greens and browns of the canopy, while others advertise with bright patterns that signal danger. In tropical systems, warning coloration is not random decoration. It is a communication strategy shared among unrelated species through a phenomenon known as Mullerian mimicry. When multiple toxic species converge on similar color patterns, predators learn more quickly and avoid them all. The cost of educating a predator is shared. Your inflamed skin is part of that education, even if you are not the intended student. Heat intensifies the experience. In a humid rainforest, body temperature regulation depends heavily on peripheral blood flow and sweating. When you flush hot water over the affected skin in an attempt to soothe it, vasodilation increases. Blood flow to the area rises, potentially accelerating the distribution of venom compounds within superficial tissues. The warmth can heighten the sensation of burning because temperature-sensitive nerve fibers overlap with pain pathways. What feels like relief in the moment may amplify inflammation minutes later. Friction from rubbing or from tight clothing compounds the mechanical damage, breaking more spines and pressing venom into freshly compromised skin. The instinct to attack the discomfort becomes the mechanism that sustains it. Around you, the forest continues its layered negotiations of risk and survival. Ants patrol the same leaves that host the caterpillars, sometimes forming mutualistic relationships with plants that provide nectar in exchange for defense against herbivores. Birds scan from mid-canopy perches, selecting prey based on size, movement, and previous experience. Some specialized predators have adapted to consume toxic caterpillars by targeting less venomous body segments or by shaking them violently to dislodge spines before ingestion. These behaviors reflect an evolutionary arms race in which chemical defenses are met with behavioral countermeasures. The caterpillar's spines are not invincible, but they are effective enough to shift probabilities. As hours pass, the affected area on your skin pulses with intermittent waves of pain. The immune system continues its work, dispatching cells to engulf foreign material and repair tissue. Yet, embedded spines can remain lodged until they are physically removed or shed with normal skin turnover. Each time fabric drags across the site, a faint resurgence reminds you that the forest's defenses are not always visible. The clothing you wear, designed for protection, has become a secondary vector. In field research protocols, experienced biologists treat such exposures with adhesive tape to lift superficial spines, avoid rubbing, and wash gently with cool water to limit further spread. The goal is containment, not aggression. The broader ecological narrative emerges in quiet details. Caterpillars are not merely transitional forms on their way to becoming butterflies or moths. They are primary herbivores shaping plant communities. By consuming leaves, they influence growth patterns, nutrient cycling, and the competitive balance among plant species. Their toxins and spines are investments in reaching the pupal stage, where metamorphosis will reorganize their tissues into winged adults capable of dispersal and reproduction. The pain you feel is collateral in a larger life history strategy aimed at surviving long enough to migrate, mate, and lay eggs on suitable host plants. Many species are highly selective, choosing specific plant genera whose chemical compounds they can tolerate or even sequester for their own defense. This tight association between insect and plant is a product of coevolution, a dialogue written in leaf chemistry and larval physiology. In this corridor of leaves, the lesson is not simply that something hurts. It is that the forest is structured around layered feedback loops. Touch triggers defense. Defense triggers inflammation. Reaction spreads defense further. The caterpillar does not chase, does not strike, does not roar a warning. It waits, relying on stillness and structural design. Your discomfort is a testament to the efficiency of that design. What appears soft and vulnerable is in fact armed with microengineering refined over millions of years. The irritation that widens across your skin mirrors the expanding awareness that survival in this ecosystem depends as much on restraint as on movement. In the rainforest, the smallest organisms can impose the largest lessons, and every leaf corridor carries both shelter and consequence woven into the same green fabric. The forest does not advertise its corridors in straight lines. Instead, they appear as subtle compressions in vegetation, places where repeated passage has pressed leaf litter flat and polished roots smooth. These are not human trails, but arteries of movement shaped by hooves and muscle over years. In the lowland rainforest, herds of peccaries, compact muscular ungulates with bristled coats and pale collar markings, travel these routes between feeding grounds, wallows, and water sources. Their presence is often announced first by scent, a musky, resinous odor produced by dorsal scent glands that mark territory and reinforce social bonds. The air carries it before the animals come into view. You step through a curtain of lianas and find yourself inside one of these corridors without recognizing it. The undergrowth seems briefly quieter, then trembles with sound. Leaves rattle, not with the delicate patter of small mammals, but with a rolling surge, as if the forest floor itself has gained momentum. A herd of collared peccaries moves as a cohesive unit, Bodies low and compact, heads aligned, tusks barely visible beneath lips that twitch with alertness. Their eyesight is modest, but their hearing and sense of smell are acute. A sudden human presence at close range is interpreted not as a neutral anomaly, but as a potential predator intrusion. Peccaries are prey for apex predators such as jaguars, and their defense logic is shaped by that pressure. When threatened, individuals do not scatter blindly in all directions. Instead, they bunch tightly, presenting a wall of bodies and snapping jaws. The herd becomes a single organism, its strength derived from numbers and coordination. Alarm grunts ripple through the group, and the animals pivot toward the disturbance. In open terrain, a human might step aside and allow the herd to pass. In dense understory, there is no open terrain. The second mistake arrives in response to that surge. Running seems instinctive, a sprint away from mass and sound. Yet sprinting in a cluttered rainforest without a clear lane is a wager against physics. The ground is uneven, threaded with roots that rise like ribs from the soil. Fallen branches lie half-hidden beneath leaf litter. Vines loop at ankle height. Visibility extends only a few meters before dissolving into green shadow. To accelerate blindly through this space is to trust that obstacles will align with your stride. Within seconds, a foot catches on a root. The body pitches forward. If momentum carries through, the chest may slam into a trunk or the ground, air driven forcefully from lungs in a blunt exhalation. The diaphragm spasms, refusing immediate cooperation. Alternatively, a leg may collide with a sharpened branch, producing a puncture wound that bleeds freely in the humid air. The peccaries did not strike. They triggered flight. The terrain delivered the blow. Humidity transforms sprinting into metabolic strain. Tropical air holds moisture that impedes evaporative cooling. Sweat accumulates rather than evaporating efficiently, and core temperature rises. A panic sprint elevates heart rate and respiratory rate sharply. Oxygen demand spikes as large muscle groups engage. In a cool, open field, this demand might be sustainable for short bursts. In a saturated understory with air already heavy and thick, hyperventilation can lead to dizziness. Carbon dioxide levels drop, altering blood pH and contributing to lightheadedness. The phrase "gas out" is literal. Oxygen delivery becomes inefficient just as coordination is most needed. The herd's logic remains consistent. Peccaries are not built for prolonged high-speed chases. They are built for forceful, short-range defense. Their shoulder muscles are robust, their necks thick, their canines sharp enough to inflict serious injury at close quarters. In a tight group, they may charge as a mass to push a threat away from their center. Once the perceived danger retreats beyond immediate proximity, the herd regains formation and continues along its route. Their objective is not pursuit, but protection of young and maintenance of cohesion. Ecologically, peccaries are ecosystem engineers. Their foraging disturbs soil, aiding in seed germination and nutrient mixing. They consume fruits, seeds, roots, and occasionally small animals, influencing plant community composition. By trampling and rooting, they create microhabitats for insects and alter understory structure. Their corridors are not random. They link resources in patterns shaped by seasonal fruiting cycles and water availability. During dry periods, herds may concentrate near remaining water sources, intensifying use of specific paths. These movement patterns form a spatial memory within the landscape. When you stumble into such a corridor, you intersect with that memory. The herd recognizes the path as a line of security and familiarity. Your presence is the anomaly. Running full speed through dense vegetation not only risks collision, but also removes the opportunity to read the herd's direction. Often, stepping calmly aside, allowing the group to pass while maintaining visual awareness, reduces escalation. Panic sprinting, by contrast, increases the chance of crossing the herd's line of movement repeatedly, prolonging perceived threat. As oxygen debt accumulates and lungs burn, decision-making narrows. The chest, recently slammed against a trunk, aches with each breath. A leg puncture oozes, mixing blood with soil that harbors bacteria and fungal spores. The combination of breathlessness and pain can induce a sense of urgency that overrides careful foot placement. Each additional misstep compounds strain. Muscles fatigue more quickly in humid heat, and lactic acid builds in tissues. Once coordination degrades significantly, the risk of a more serious fall increases. Predator-prey dynamics illuminate the herd's behavior further. Jaguars, capable of isolating and overpowering individual peccaries, rely on stealth and precise timing. The herd counters with vigilance and mutual defense. Their alarm calls are not mere noise, but signals that synchronize movement. In some cases, herds have been observed surrounding and harassing predators until the threat retreats. This collective aggression is effective because it concentrates risk on the predator rather than dispersing it across individuals. The same collective surge that deters a jaguar can intimidate a human who misreads it as pursuit. The forest itself compounds the scenario. Understory vegetation limits long sightlines. Sound reverberates unpredictably between trunks. The thud of hooves against damp soil can seem closer or farther than reality. In this acoustic maze, panic amplifies perception. A sprint driven by fear ignores terrain memory and the herd's likely path. Escape becomes self-injury because the environment is structured to slow and redirect movement, not facilitate straight-line flight. Thermoregulation again plays a silent role. Peccaries dissipate heat through behavioral means, seeking shade, wallowing in mud to cool and deter parasites. Humans in similar humidity rely on sweat, which underperforms in saturated air. A rapid sprint elevates core temperature, and without effective cooling, endurance collapses quickly. Once exhausted, recovery is slow in oppressive heat. Breath knocked out by impact adds a mechanical barrier to oxygen intake. The combined effect is a narrowing of options. As the herd's sound recedes and the corridor returns to relative quiet, the escalation becomes clear. The peccaries did not need to make contact. Their defense logic relied on cohesion and momentum. The injury emerged from misaligned response, full-speed retreat through terrain designed for measured navigation. The lesson embedded in the encounter is not about the ferocity of peccaries alone, but about the mismatch between herd dynamics and individual panic. In dense rainforest, survival depends less on outrunning and more on reading movement patterns and respecting established pathways. The corridor remains, leaves settling back into place. The herd continues its cyclical route, perhaps pausing to feed on fallen fruit before moving toward water. The ecosystem absorbs the disturbance. For the human who intersected that path, the realization lingers that in humidity and clutter, oxygen is currency and footing is fragile. Panic sprinting spends both recklessly. When breath is gone and balance compromised, the jungle does not need to pursue further. It has already claimed its leverage through terrain and physiology intertwined.